Welcome to the Group 12 presentation on map coloring. This is a presentation created by Alexandra Lingenfelter, Leisha Peralta, and Sofia Taveras. So let's just go ahead and get started. So let's take a look at map coloring. The foundations of map coloring are built upon graph theory. Here, the four-color problem, which states that any map with contiguous states can be colored using a four-color mapping, and the Kempe chain, which is pictured on the left here, showcasing a simple sort of circuit which connects each and every point around the perimeter with a similar color, whereas any point in which there is a higher degree than 2 must be connected with a different color. And together this creates the basis for recontextualizing a map into a colorable graph based upon the switch of faces to vertices, with the relationships of borders being classified by edges. So as you can see below, a sample map of Germany and its individual states has been transformed into a graph suitable for discovering the needed amount of colors to fill in each state without having any two colors touching by a shared border. So here with our map of Germany, I will just showcase this to you with my cursor very quickly. So in the sample map, each has been transformed into a vertex. These little circles here are representing different vertices, and where lines connect, states touch by borders. So for example, this state here at the top is connected to a small orange state, it is connected to a teal state, and it is also connected to a purple state, having a degree of 3. So in our next slide, we'll showcase the transformation of a sample map of states using the country of India and kind of going through this process and showcasing the logistics of graph theory and cartography to develop a final product based upon the four-color problem and knowledge of how geometric patterns influence our understanding of vertice-edge relationships. So here is a redrawing of a map utilizing graph theory. This is a sample map of India, and notice that each of these states has been represented by a vertex, which, as you can see here, are each of these little individual circles, like was in the Germany state map. And these can be referred to as a sort of face to vertex conversion. So each face, each individual state that you see on the left side map is being depicted by a circle here. And the borders, where there are common borders, they have been connected via an edge, which is just this line here. And this indicates how many states have a conjunction or a common border with one another through the amount of edges that come off of one vertex being the degree. Moving on to our next slide, we have discovering how many colors are needed. In order to determine a needed amount of colors, one must first look for any geometric shapes that appear in the new graph. So we can use these sort of as a clue. And at the very top of the map of India that we have here, we clearly have a triangle. This sort of triangular shape indicates that we're going to need 3 individual colors as we're having a geometric pattern. As you can see here, there's a triangle here and a triangle here. We just use this one as a sole example. But there are obviously others within this graph that showcase we have a triangular sort of relationship occurring here, and we're going to need 3 colors. And as such, when we begin the process, we want to use this framework to help us move around the map, see where points of highest degree exist, like I had mentioned previously, how many edges come off of one point, and we can see how many colors that we might need to use to connect these points without any two similar colors ever sharing an edge, which eventually becomes a border when coloring in the map completely. So this is achieved through either labeling each vertex with a letter or a colored dot to indicate that it has been accounted for during this process. So for our example, rather than writing a bunch of individual letters like B for blue and Y for yellow, we instead decided to just do the contiguous states and make it a little bit easier and more visually appealing by utilizing dots. So after the process of moving around the map via trial and error, one might find it far more beneficial to compare the original map with the redrawing that was completed using the principles of chromatic numbers and the Kempe chain. So like I just mentioned, this image right here indicates this. Chromatic number, as we have discussed in class before, simply talks about the ways in which we understand how faces can have individual colored values and no two borders touching. So very similar to map coloring here. And lastly, we will showcase this process through an application of the concept altogether through the states of Mexico. So one last time, we see all of the individualized states here. And then within our second image, as indicated by this transitional arrow, we have each and every state connected with one single vertice and an edge that connects all of the states that are touching one another. So in completing this graph, we look for states with high degrees. So this area right here is concentrated by states having very high degrees, meaning that they have the most edges coming off of one vertex. Well, coming off of one vertex, excuse me. And we use these to create one singular map where every single dot represents a different color with no two edges sharing a state that has the same exact color. So thank you so much for your time, and I hope this was a helpful way for you to better understand graph theory and why approaching coloring a map in this way is effective for making sure that information is easily accessible and readable in our maps.